Hello everyone, welcome to Exemplar Physics. In the last video, we have discussed about measurement, why a standard unit is required for measurement, what are the fundamental physical quantities as defined by General Conference of Weights and Measures, what are its units and symbols. If you haven't seen that video, I request you to watch the video first. In this video, we'll be discussing about derived quantities and supplementary quantities. So let us start our discussion. So first topic which we are going to discuss is derived quantities. Derived quantities are those physical quantities whose units are derived from, or we can say expressed as combination of base units. Those physical quantities whose units are derived or expressed as combination of base units are called derived quantities. So this combination is generally as multiplication or division or both multiplication and division of base units. So this is how they are combined. So let us take few examples to understand the derived quantities, and also along with the derived quantities, let's understand their units. So I'll try to write it in a tabular form. So on one side we'll have derived quantities, on the other side we'll be having its formula and SI unit. So let us start with the most basic one, that is area. So area, as you all know, is defined as length into breadth. What is the unit of length? Unit of length is meter, and the unit of breadth is also meter. So meter into meter is meter square. So SI unit of area is meter square. So meter square is a derived unit. So area is derived quantity. So area is defined as the product of two lengths, hence derived quantity. Let's take one more example. Let us number it as 1. Let us take one more example. Example 2, volume. So volume is defined as length into breadth into height. So unit of length is meter, unit of breadth is meter, and unit of height is again meter. So the basic quantity or the fundamental quantity length is been measured 3 times, is been combined 3 times as a product, meter into meter into meter, this gives us a meter cube. Let's take one more example. Mass density. Mass density. So the formula for mass density is mass per volume. So what is mass per unit for mass? Unit for mass is kg. Unit for mass is kg and unit for volume is meter cube. So the unit is kg per meter cube for mass density. Next, frequency. Frequency. The formula for frequency is 1 by time period. So 1 by time period, unit for time period is second. So 1 by second. So the unit is per second, or a special name is given to this as hertz. HERTZ. Okay, hertz is a name of a scientist, hence H you have to write always as capital while writing its symbol HZ. So H has always should be written as a capital. Next, speed. Speed is defined as distance per time taken. So unit for distance is meter and unit for time is second. So the unit is meter per second. So that is the unit for. So this is derived unit, right? This distance is a fundamental quantity, that is length, and the time is a fundamental quantity. So the combination for distance and time, distance upon time, is the derived quantity. Speed is derived quantity. Next one, sixth, velocity. So velocity is defined as displacement per time taken. So what is the unit for displacement? Meter, same as that of the distance, meter, and the unit for time is second. So the unit is meter per second. So velocity is also a derived quantity. Let's take few more. Seventh one, acceleration. Acceleration formula is change in velocity by time taken. So unit for velocity is meter per second. So unit for time is per second. So we'll get a meter per second square. So this is the SI unit for acceleration. Next, force. Force is defined as mass into acceleration, product of mass and acceleration. So unit for mass is kg, unit for acceleration is meter per second square. So kg, meter per second square, is the unit for force, and this quantity is also written as capital N. That is the symbol for Newton. So Newton is the unit for force, which is kg meter per second square. So this unit is given a special name on the name of the scientist Newton. Let's take one more. Ninth one, work. Work is defined as force into displacement, product of force and displacement. So force itself is a derived quantity into some another derived quantity. So force is unit for force is kg meter per second square, and unit for displacement is meter. So the unit becomes kg meter square per second square. Or if you write kg meter per second square as Newton, then Newton into meter, the unit becomes Newton meter. Or this term, this unit kg meter square per second square or Newton meter is given a new name, and the new name is Joule, again named after a scientist. So J should be capital. And power. Power is defined as work done per time taken. So unit for work done is, you already know, joule, and unit for time is a second. So the unit becomes joule per second, and a new unit is given to, or joule per second is called as watt. Capital W, again name of a scientist, watt. So how do you understand whether a given quantity is derived or fundamental quantity? Derived quantities are always expressed as a combination of two or more fundamental quantities. So if you see in all the 10 examples which I have given here, all of them can be expressed in terms of fundamental quantities. Hence, they are called as derived quantities. They are derived from fundamental quantities. I hope that you have understood what are derived quantities. Let us start our discussion on supplementary quantities. If you are noting down, you can pause the video and you can note it down at any time. Now let us discuss supplementary quantities. We have already learned that 7 basic quantities or fundamental quantities were considered by General Conference of Weights and Measures. There are 2 quantities which are considered as supplementary quantities. There are 2 quantities which are considered as supplementary quantities. They are not considered either in fundamental quantities or derived quantities. So they are considered separately. So there are 2 supplementary quantities. The first one is called plane angle. The first one is called plane angle. So for plane angle, we need to draw a circle. let's say this is a circle with center, let us name it as O, and this is the radius of the circle is, let's say, R. So we need angle, right? Plane angle. So we need an arc. Let us name this arc as AB. So AB is our arc and the angle subtended by AB at the center, let us call that angle as d theta. Let us call that angle as d theta. So the plane angle is nothing but this d theta, the angle subtended by the arc AB. And let's say the length of this arc be ds. Length of this arc, this length is ds. So plane angle d theta is defined as arc length by radius. Arc length by radius. So arc length is equal to, we have taken it as ds and the radius is r. So d theta is equal to ds by r. So this is the plane angle, definition for plane angle. Unit for plane angle is radian. Unit is radian and its symbol is RAD, rad. We don't measure it in degrees, we measure it in radians. So this is plane angle. And the second one which we have is called solid angle. Second one which we have is solid angle. So it's to understand solid angle, what you need to consider is, you need to consider a sphere. So this is, consider this as a sphere. Okay, not circle but sphere, 3D structure. So what you need to do is, you need to take a surface area. You need to consider a surface area, small surface area. Let's say this surface area is dA. This surface area is dA and the sphere is having the radius of r. So the angle subtended by this surface area, let us say that is a solid angle. Let us say that solid angle is equal to d omega. I don't know whether you are able to understand or not. Just I'll give one analogy and try to understand the solid angle. Suppose you have a spherical watermelon. Okay, so this is a spherical watermelon. Consider this as a spherical watermelon. From the watermelon, what you do, you cut a small slice such that you cut a small slice out of this watermelon. So the outer part will be green, right? So you cut a small slice of the watermelon such that this slice touches the center. When you take out the slice would look something like this. When you take out that slice, the slice would look something like this. and this angle which has been made, by this surface area at the center we are calling that as d omega here. So that is the solid angle. This is the solid angle. Remember, it should touch the center. So this surface area we have taken it as dA, and the radius is r. Radius of the sphere is taken as r. So solid angle is defined as d omega is equal to the ratio of the surface area dA which is subtending angle at the center by r square. So this is how the solid angle is represented. So unit for the solid angle is unit is steradian. Okay. So where do we use plane angle? Plane angle is used in rotational mechanics. Plane angle is used in rotational mechanics. And this solid angle is used in radiometry and photometry. So when we will be discussing those topics, we will be talking about them. So these are the two supplementary quantities which we have: plane angle, unit radian, and solid angle, unit steradian. So just understand the definitions of both the supplementary angles. One thing to be noted here is the supplementary angles are dimensionless quantities. They are dimensionless quantities. Both radian and steradian, or plane angle and solid angle, are dimensionless quantities. So what is the meaning of dimensions in physical? Dimensionless quantities or dimension in physical quantities we'll discuss in the next video. So I hope you have understood what we have discussed in this video. If you still have any doubts, please write it in the comment section. I'll surely help. If you like the video, please share it with your friends. Thank you. Bye bye.